There is a point of light in the southern sky. Navigators steered by it for millennia. Every major telescope ever built has been pointed at it. Scientists, filmmakers, mission designers, all of them treated it as the most familiar address beyond our own sun. It was the one place everyone assumed they already understood. And in August 2024, the James Webb Space Telescope looked at it for the very first time. What it found was not confirmation. It found something hidden inside the habitable zone. Faint, almost impossibly faint, in a place no instrument had ever been sensitive enough to check. Then, months later, it looked again. The thing was gone. That point of light is Alpha Centauri, the nearest sun-like stellar system to Earth. And the question Webb just forced open is one that should have been asked much sooner. What else has been hiding there, in the most watched place in the sky, that no one was ever able to see? The Milky Way stretches roughly 100,000 light-years across. It contains somewhere between 200 and 400 billion stars, scattered across a disk so vast that light itself takes 100,000 years to cross it edge to edge. Alpha Centauri sits 4.3 light-years away. If the galaxy were the size of the North American continent, Alpha Centauri and the solar system would share the same city block, the same handful of square meters on a map that spans a continent. At the scale of the universe, these two systems are practically on top of each other. Alpha Centauri is not one star. It is three. Alpha Centauri A and B, two sun-like stars locked in a gravitational embrace, orbiting each other every 79.9 years. Alpha Centauri A is slightly larger than the Sun, roughly 50% more luminous. Alpha Centauri B carries about 90% of the Sun's mass. Together, they form the closest binary pair of sun-like stars to Earth in the entire galaxy. Far out on the fringes, barely gravitationally bound, a dim red dwarf called Proxima Centauri completes the trio. Invisible to the naked eye, despite being the single closest individual star to the solar system. For generations, this system has been the default destination for every serious interstellar concept. Breakthrough Starshot designed spacecraft to reach it within a human lifetime. James Cameron placed Pandora in orbit around a gas giant there. Liu Cixin's The Three-Body Problem used it as the origin of an alien civilization. Every single one built on the same assumption, that Alpha Centauri is not just reachable, but knowable. That the nearest star system must also be the most understood. That assumption was never tested, it was inherited. And Webb, when it finally looked, did not confirm the inheritance. It dismantled it, beginning with a number the scientific community had quietly carried for decades without being able to explain. That number was 0. 0 confirmed planets orbiting Alpha Centauri A. 0 confirmed planets orbiting Alpha Centauri B. hold that against what else astronomy has accomplished. As of 2024, astronomers have confirmed more than 6,000 exoplanets. Planets around stars thousands of light years away. Planets smaller than Earth. Planets whose atmospheric chemistry is already being analyzed by the same telescope that just observed Alpha Centauri. 6,000 confirmed worlds. And the nearest pair of sun-like stars, blazing as the third brightest point in Earth's night sky, so close that serious scientists have proposed reaching it within a human lifetime, has yielded. Nothing confirmed. Proxima Centauri has done marginally better. 3 planets, 1 in its habitable zone. But Proxima is a violent, flaring star that strips atmospheres from anything orbiting close enough to receive warmth. Its planets do not answer the question that has always mattered most. Do sun-like stars in the nearest system host worlds of their own? The most famous attempt at an answer came in 2012. A European team announced an Earth-mass planet orbiting Alpha Centauri b, the nearest exoplanet ever found. Headlines exploded worldwide. It was not real. The binary system's gravitational noise had been subtracted imperfectly, and what remained mimicked a planet with disturbing precision. Alpha Centauri b, a planet that made global news, does not exist. Other campaigns followed. Every major detection method, every decade, progressively sharper instruments. The same answer every time. Nothing confirmed. And the reason had nothing to do with an absence of planets. It had to do with a property of this system that turns out to be the exact opposite of an advantage. When people imagine studying a star, they picture a telescope aimed at a distant pinpoint. Distant meaning dim, dim meaning manageable, manageable meaning faint planetary signals might emerge from the noise. That logic works for the vast majority of stars. It does not work for Alpha Centauri. Alpha Centauri A blazes as the third brightest object in Earth's entire night sky. A planet in its habitable zone would be roughly 10 billion times fainter than the star in visible light. 10 billion. Every streetlight in every city on Earth gathered into a single point, aimed at a camera lens. Beside it, a single candle. The camera is trying to photograph the candle. That is the contrast astronomers are working against. And beside Alpha Centauri A sits Alpha Centauri b, a second sun-like star, blazing from a different position, adding its own overwhelming glare. When the two stars reach their closest orbital point, their light merges into a single, unresolvable wall. 2 floodlights side by side, and somewhere between them, perhaps, a firefly. Every detection method breaks against this. Radial velocity creates noise thousands of times larger than any planet could produce, which is exactly what generated the false detection of 2012. Transit photometry requires geometric alignment with a 1 in 200 probability. Direct imaging demands precision that Alpha Centauri's brightness makes nearly impossible. The sharpest illustration, TRAPPIST-1, a dim ultra-cool red dwarf roughly 40 light-years away, nearly 10 times farther than Alpha Centauri, has 7 confirmed rocky planets, 3 in the habitable zone. Webb is already analyzing their atmospheres in molecular detail. Worlds 10 times farther away turned out to be easier to study. The nearest turned out to be nearly impossible. That inversion is why it took until 2024 for any instrument to seriously attempt what Webb attempted. Every Webb observation begins with target acquisition, the automated process by which the guidance system locks onto a star and confirms alignment. It has worked flawlessly for thousands of targets since 2022. For Alpha Centauri A, it failed before it could start. Webb's guidance sensors would saturate instantly if pointed at it directly, flooding with light, losing all orientation. So the team built a workaround with no parallel in Webb's history. They pointed the telescope at a completely different star, Epsilon Muscae, a red giant, 330 light-years away, locked onto it, confirmed alignment, then commanded Webb to rotate a pre-calculated angular distance to where Alpha Centauri A should be, placing the star behind the coronagraphic mask by mathematics alone, without ever seeing it. The margin for error is measured in fractions of an arcsecond. If Alpha Centauri A lands slightly off-center, starlight leaks around the mask and floods the detector. The observation is destroyed. They got it right. With Alpha Centauri A hidden behind the mask, Webb's MIRI instrument began collecting light at 15.5 microns, deep in the infrared, invisible to human eyes. At this wavelength, the contrast between a sun-like star and a warm gas giant drops from billions to 1 to roughly 10,000 to 1. Still extreme, but within the range where extraordinary effort might yield something. The coronagraph does not produce a clean black circle. It produces rippling halos, diffraction rings from photons bending around the mask edges, overlaid with scattered light from the telescope's mirrors and struts. Every ring, every spike is indistinguishable from a faint point source. Then, there is Alpha Centauri B, still blazing, pouring its own rings and artifacts onto the detector, layering them over the contamination from Alpha Centauri A. What the instrument records is not an image. It is a layered accumulation of competing signals, each one potentially real, each one equally possibly not. The team stripped it away, pass by pass. Reference stars to model the contamination, algorithms to subtract Alpha Centauri B. Each layer peeling back, each subtraction carrying its own uncertainties. And when the last layer came off, something was there. Its brightness was more than 10,000 times dimmer than Alpha Centauri A. If Alpha Centauri A were a concert arena with 10,000 people screaming, this source would be one person in the back row whispering. Webb heard it. The team labeled it S1. They tested it against every alternative. Background star. Alpha Centauri moves rapidly across the sky. Any background object would shift position between observations months apart. No known source existed at that location. Foreground asteroid? The geometry made this very unlikely. Instrumental artifact. This one was harder to rule out. The standard method Angular differential imaging, rolling the telescope slightly between observations, was unavailable. The roll maneuvers did not execute as planned. The team ran alternative analyses instead, comparing S1's properties against known artifact signatures, testing its brightness and position against instrumental models. Their conclusion: S1 was unlikely to be an artifact. The most probable explanation was a real astrophysical source, physically associated with Alpha Centauri A. But unlikely to be an artifact is not the same as confirmed planet. S1 was classified as a candidate. The signal is real. Something produced it. What that something is remains open. If S1 is a planet, a gas giant with mass roughly comparable to Saturn, orbiting between 1 and 2 astronomical units from Alpha Centauri A, on an elliptical path that carries it alternately in and out of the habitable zone. Period estimated between 1.5 and 3 Earth years. Inclination steeply tilted, roughly 50 to 130 degrees, relative to the binary plane. Sitting, if real, in the habitable zone of the nearest sun-like star to Earth. There was also an older signal buried in the literature, sitting unresolved for 4 years. In 2019, a team used the Very Large Telescope in Chile to observe Alpha Centauri A for roughly 100 hours with a purpose-built coronagraph called NEAR. A faint source appeared at approximately 1.1 astronomical units, designated C1. Inconclusive, too short an observation arc to determine if it moved like a planet. Published in 2021, never confirmed, never ruled out. Then Webb found S1. Different telescope, different instrument, different wavelength. Same system, same star, same mass range. Could C1 and S1 be the same world, seen 5 years apart from 2 completely different instruments? The orbital models said yes. A single planet with mass between 90 and 150 Earth masses, period between 2 and 3 years, eccentricity near 0.4, could account for all 4 data points. 2 instruments, 5 years apart, converging on the same location in the habitable zone of the nearest sun-like star. The team looked again. In February 2025, Webb looked again. Same instrument, same coronagraphic mode, same processing pipeline. S1 was not there. In April 2025, Webb looked a third time. S1 was still not there. The team checked everything. The February and April data were clean. The instrument performed exactly as designed. S1 had simply vanished. In most scientific contexts, this ends the story. One detection followed by 2 non-detections is the signature of a spurious signal. The team did not accept that. They turned to orbital geometry. A planet on an elliptical orbit does not stay fixed relative to its star. At some points, it swings far enough from Alpha Centauri A to be detectable. At others, without being physically behind the star, its projected separation, as seen from Earth, drops below the coronagraph's inner working angle. At that point, it disappears into the residual glare, not because it is gone, because the geometry hides it. The team simulated millions of possible orbits, each consistent with the August 2024 detection. Each tested against the February and April windows. The result? In 52% of dynamically stable orbits consistent with the August detection, more than half, the planet moves inside the coronagraph's blind zone during both follow-up windows. 52%. More than half of all plausible orbits predict exactly the disappearance that was observed. The non-detections were not evidence against S1. They were consistent with a real planet that had moved somewhere the instrument could not follow. August 2024 says where S1 was. February and April 2025 say where it was not. Together they constrain the orbital solution, eliminating impossible paths, leaving only those consistent with all three outcomes at once. The candidate survived. It did not become confirmed. And between candidate and confirmed lies a gap that contains something larger than one planet. S1, if real, is a Saturn mass gas giant, roughly 95 times Earth's mass. That sits near the lower boundary of what Webb can detect at Alpha Centauri's distance. That is the flaw. Below S1, the detection capability does not taper. It drops away. A Neptune mass planet falls below the noise floor entirely. A rocky planet the size of Earth, in the middle of the habitable zone, would sit at thousands of times below the detection threshold. Not as a faint smudge, as nothing. The worlds that matter most for the question of life around the nearest sun-like star are precisely the worlds that cannot be seen. Consider the inverse. An astronomer at Alpha Centauri, using a telescope equivalent to Webb, studying the solar system from 4.3 light-years away, would find Jupiter above the sensitivity threshold. Saturn, marginal, right at the edge. Everything else, nothing. Earth registers at thousands of times too faint to detect. 4 billion years of biological complexity produces no signature of any kind visible from this distance. That astronomer's complete inventory of the solar system would account for roughly 30% of its total planetary mass and 0% of the worlds where liquid water exists. 0% of the worlds where life has ever appeared. That is the exact situation facing any observation of Alpha Centauri A today. The system could contain a full architecture of rocky worlds, with oceans, weather, geology, and perhaps something more, and not one of them would appear in the data. Not as faint candidates, as nothing. The nearest sun-like system is not revealing itself. It is accumulating questions. And there is one question sitting underneath all the others, one that the data cannot answer, and that most people have not thought to ask. If something exists in that system, capable of looking outward, capable of detecting the faint thermal signature of a warm planet orbiting a nearby sun-like star, it has had billions of years to do so. From Alpha Centauri, Earth is detectable, not as a civilization, not as a biosphere, just as a point of warmth at the right distance from the right kind of star. The same kind of signal humanity has been unable to detect coming from Alpha Centauri. The observation runs in both directions. Humanity has been pointing telescopes at Alpha Centauri for generations, assuming it was the one doing the looking. That assumption was never tested either. For 3 decades, astronomers have assembled a statistical picture of how common planets are. Roughly 1 in 5 sun-like stars appears to host a rocky planet in its habitable zone. The Milky Way could contain billions of potentially habitable worlds. This picture was built from thousands of confirmed detections, and it has a hole in the middle. Every model built from Kepler, TESS, and decades of surveys, all of it constructed from data that explicitly excludes the nearest and most important test case. Alpha Centauri contributes nothing to these numbers. 0 confirmed planets from Alpha Centauri A, 0 from B. 1 candidate that appeared and vanished. August 2026 is approaching. Webb's orbital models make a specific, testable prediction. If S1 and C1 are the same planet, S1 should return to a visible position in that window. A planet on a real orbit will be there. An artifact will not. An artifact does not follow orbital mechanics. Dust does not obey Kepler's laws. A ghost does not reappear on schedule, at the predicted coordinates, at the predicted brightness. If S1 appears where the equations say it should, the nearest sun-like star just gained its first confirmed planet. If it does not appear, the blank space deepens. Either way, the question underneath will remain. There is a point of light in the southern sky. That is where this story began. Webb looked beneath its glare, and the star did not behave like something known. It behaved like something keeping secrets for the entire duration of human observation, hidden not in darkness, but in brightness. Not in distance, but in proximity, in plain sight and unreachable at the same time. Alpha Centauri A is the nearest twin of the Sun that exists. Same spectral classification, same nuclear processes, same surface temperature. The nearest star in the galaxy that resembles in every property science can measure. The one star known to have produced conditions where life emerged. Whether it has anything comparable orbiting it, anything in the region where water stays liquid, where chemistry accumulates across billions of years, where something might eventually look back, is a question that remains genuinely open. Not almost resolved. Open. And the not knowing carries a weight that not knowing about any other star cannot match. Because this star's light reaches Earth in just over 4 years. Because spacecraft designs already exist to reach it within a human lifetime. Because what orbits it sits within the outer edge of what human technology could, in principle, one day reach. What is out there? Right next door, in a place humanity has been watching for thousands of years without ever truly seeing. Every clear night, Alpha Centauri rises in the southern sky. It blazes with the steady light of 2 sun-like stars, unchanged, exactly as it has appeared to every generation that looked before this one. To the naked eye, it looks like something known. But beneath that light, something may be moving. A world on an orbit nobody predicted. Elliptical, tilted, sweeping through the habitable zone and back out again, appearing in the data once and then retreating behind a wall of glare, no instrument has yet fully penetrated. And beneath that world, deeper still, past every threshold current technology can reach, there may be others, smaller, quieter, impossible to see, worlds that would register from this distance as nothing at all. Humanity built entire stories around this star, pointed every instrument it ever made at it, assumed across centuries of watching that closeness meant comprehension. And when the sharpest eye ever built finally looked beneath the glare, the star did not answer. It only showed how much had always been hidden there. How much is hidden still. So here is the question worth sitting with tonight. If the most watched star in the sky has been hiding worlds we could not see, what else have we been staring at for centuries without ever truly looking? If this made you see the night sky a little differently, that is exactly what this channel is for. Hit like if you want more, and subscribe so you do not miss what comes next. Because in August 2026, Webb looks again. And whatever it finds, or does not find, we will be here to tell you.